The speaker for today's talk is Dr. Abdullah Imran, a prince. Sorry. He's a faculty member of our department. Okay, I don't know if he's a prince. The title of his talk is, as you can see, Self-Supervised Learning in Medical Imaging, okay? Effectiveness and relatedness. Okay? He will give an overview of self-supervised learning and recent development. Okay? And he will also discuss specific medical imaging examples focused on designing task domain-specific self-supervised learning techniques. Okay, let's welcome Dr. Imran.
Thank you. Thanks for that nice introduction. So, as you can see, today I'm going to talk about self-supervised learning, particularly focusing on medical imaging and how we can build task-specific or domain-specific self-supervised learning for medical imaging. So, you can see just a few months back from this tweet, someone asked what are the most important intellectual breakthroughs in AI, right, or new ideas in the past 10 years. And Ian Lecourt, as you know, one of the pioneers of deep learning, right, he actually ranked self-supervised learning as the top breakthrough, right, out of 5. So that means self-supervised learning is a big thing now. So here is the outline of my today's talk. First, I will give a quick introduction of medical imaging, then overview of self-supervised learning, what's possible with self-supervised learning, basically showing some examples from computer vision and medical imaging, and then I'll talk about specific medical imaging examples on image quality assessment, image denoising, CT organ dose estimation. Those work particularly with self-supervised learning. And then I will briefly share our ongoing work in my group and future directions. So if we look at the medical imaging workflow from this picture, right, starting from scanner or scanning the patient, then acquiring the images, image enhancement or augmentation techniques, followed by some analytics or detection, classification, finally clinical decision making. So we can separate the whole imaging workflow into 2 phases, upstream and downstream. Upstream phase actually focuses on more like image generation. On the other hand, downstream phase focuses on image analysis. And with the advancement of AI and deep learning, particularly in computer vision, we can actually leverage those techniques or recent developments also in medical imaging. But we need more specific focus for this particular applications in medical imaging. So here is some quick overview of some of the work in medical imaging. For example, top left, you can see from input X-ray, we can do vertebral segmentation, spinal X-ray, and then vertebral labeling to measure the curve angle, which is the standard for scoliosis diagnosis, and finally we can also quantify the scoliosis disease based on the curve angle measured, so in terms of the severity. Then we can also do segmentation, like medical image segmentation in 3D, like volumetric segmentation of chest CT scan, basically segmenting the 5 lobes. So human lungs have 5 lobes in 2 lungs. So we can segment all lobes, all 5 lobes in one forward pass of the model, just providing the whole 3D volume in the deep learning model. Then this shows the segmentation of diabetic retinopathy image for vascular segmentation. And here, detection of nodule, which can be cancerous or non-cancerous, but first nodule detection is very important. Then image generation. You know, generative AI is currently a big thing. So we can take advantage of generative AI for medical imaging, particularly considering the data in medical imaging domain is very limited. So synthetic data could be exploited in case of medical imaging applications to augment our training data. And then this one shows image denoising. So there are many concerns about CT scanner, basically considering the radiation exposure. So to reduce the dose, the image quality could be degraded. So we need to enhance the images or remove the noises which incurred due to the reduced dose. So image denoising is an important in medical imaging. Then finally, this shows classification or diagnostic classification from chest X-ray images like normal, bacterial, or viral pneumonia. And we can also do COVID-19 classification similarly. Now, I will start talking about self-supervised learning. So self-supervised learning, or in short we can call it SSL, can help for good representation learning, which can be done unsupervised in unsupervised manner. So that means we don't need the label data for training on self-supervised learning tasks. And another interesting point is self-supervised learning can actually extract supervisory signals from unlabeled data. So that means we can actually guide the network for tasks based on data itself. So that means data itself lends labels for the self-supervised learning in case of this particular learning. And you can define that particular task, right, based on time or space. So we can use the present information to predict future, or future information to predict present, or present information to predict past, so many ways. And also here you can see from this image at the top, right? So we can pretend that we have some missing information or missing part in the image, and from the observed portion we can try to predict that missing part. Okay, so why self-supervised learning, right? So first, high quality label data set is limited, particularly for domains like medical imaging, right? There are many different challenges, like privacy issues, like considering the patient information needs to be preserved, and hospitals, they don't want to share the information or data with other hospitals or institutions, right? So we cannot just collect or curate a data set like ImageNet size, right, in medical imaging. That's just not possible. And there are annotation issues, like annotation is expensive. So deep learning models, to be effective, they require a large corpus of training label data. So to get the annotation, we need the domain expertise. So domain experts, they do the annotation manually, which is time consuming, error prone, and prone to subjectivity. So there are observer variations. So there are both inter-observer variations and intra-observer variations. So because of those issues or challenges, we cannot just have large label data set in domains like medical imaging. Then supervised learning is actually a bottleneck for building generalist models. So supervised learning actually makes the model biased towards the labels, and there is a limit for collecting the labels. So supervised learning has a limit, and that actually makes the model less generalizable. And then self-supervised learning models can transfer useful information. So we can transfer useful information from one task to another task, or one domain to another domain, or we can transfer from one data set to another data set. And according to Meta, Facebook, AI, self-supervised learning has been seen as the dark matter of AI. So in case of human or animals, we take common sense for granted. But in case of models, AI, we have to provide or build the AI models being capable of having common sense. And self-supervised learning can be that missing part and fill the gap to race towards human level intelligence. So first, self-supervised learning is very similar to transfer learning. We are all familiar with transfer learning, which is basically supervised pre-training. So where you can actually transfer knowledge from one task to another task within the same data set, or you can transfer from one data set to another data set where you don't have a large level data set like this one, or you don't have too many examples or for labels for the second task, so you can transfer knowledge from one task to another task. So let's look at a couple of examples of transfer learning. So in case of image classification, ImageNet is a huge data set of 300 billion images, natural images, and you pre-train a model, convolutional neural network model, to learn the classes in ImageNet data. And then in case of medical imaging, we can transfer the knowledge or use the pre-trained weights from the ImageNet pre-trained model, and just adding the MLP, so that can be trained from scratch, so based on the number of classes in case of our medical image data set. So this way we can use the transfer learning technique to transfer weights or knowledge from ImageNet pre-trained model to medical image data. Similarly, we can also transfer knowledge for other tasks like segmentation, image segmentation. So for image segmentation, we need the encoder part and then the decoder part. Here, in this example, only the encoder part we can use when the model is pre-trained on the ImageNet dataset. That means here they used VZ11 encoder and then added a decoder. So the encoder part is used as from the pre-trained ImageNet pre-trained model, and then the decoder part is added and fine-tuned during for particular segmentation. And here this plot show the advantage of doing this transfer learning or fine-tuning from the pre-trained weights. You can see when the model is not pre-trained, that performs poorly compared to the performance of pre-training followed by fine-tuning. And here they show compare the Jagged score, which is basically intersection over linear used for segmentation tasks. Okay, so this paper actually did a comprehensive experimentation for verifying actually if fine-tuning or full training, training from scratch, which one is useful, particularly for medical imaging tasks. Right, so they experimented with different data sets for classification, segmentation, and detection tasks in medical imaging. They actually found that fine-tuning always outperforms CNNs trained from scratch. Right, so this fine-tuning is basically from ImageNet pre-training model. And even when it doesn't outperform, at worst it performs comparably against training from scratch. So one conclusion could be made from this, right? Fine-tuning yields robust CNNs. So not only for the particular data set being used for training or fine-tuning during the fine-tuning stage, the learning could be generalized, the model could be generalized for other data. Okay, but there is a limitation with this type of transfer learning or pre-training using supervised pre-training. So supervised pre-training, as you can see, we need a supervised label data set like ImageNet. This is not possible for all other domains. So instead of doing that, we can actually do unsupervised pre-training, which is basically self-supervised learning. So in case of self-supervised learning, we can leverage the unlabeled data. Large number of unlabeled examples could be leveraged for pre-training. And this kind of pre-training is called Pretext. So we can define a task for the pre-training, which is called Pretext task, and then the model, pre-trained model is fine-tuned, which is called for the actual task, downstream task, where the evaluation will be performed. Now the question is, what type of pretext task should we use, right? And what could be possible with self-supervised learning. And the answer is there are actually many different choices, and we'll go through some of those, right? So, but in general, we can categorize them in terms of like 4 different categories. Generative models. So the generative models are by default self-supervised because they don't require any label information for the training. For example, the variational autoencoder or generative adversarial networks, again, autoregressive image generation, and diffusion, the latest models like stable diffusion. And then self-prediction, we can also predict from the data itself, right? Mask prediction, denoising autoencoder, masked autoencoder, or there is another technique like a channel shuffling, or colorization, or a split brain. Then I need relationship by pairs positioning, like relative position, jigsaw puzzle solving. Then we can also use pretext by solving these transformations like rotation or flipping. And there is this popular way of doing pretext as contrastive learning based, like simple contrastive learning representation, or simpler supervised contrastive learning, or cross-model contrastive learning. And there are actually many more. So we'll go through some of those pretext tasks one by one. First, the generative models, variational autoencoder. So, variational autoencoder is very good at variational inference, right? And they are explicit generative models. So that means you provide the data, real data is used, and to encode, and then you get the related representation when the reparameterization happens, right, by adding Gaussian noise and then sampling the noise posterior distribution. We can actually try to generate new images through the decoder, right? And since the original distribution actually cannot be known, and that's why the DE generated images will always be blurrier. And then generative adversarial networks, popular generative model, trained based on min-max game, right? Where we have a generator and the discriminator. Generator tries to generate new images, and then a discriminator will try to discriminate from the real, from the generated fake images. But in case of medical imaging, we probably should not use the term fake, but rather we could use synthetic images. Right? So GAN is implicit generative model. So that means the generator which is generating the new images, it never says the real data, the training data. It just gets the feedback from the discriminator. So the discriminator will try to maximize the likelihood for the real images coming to the model, and will try to minimize the likelihood for the images coming through the generator. And GAN-generated images could be very sharp, but there are some limitations of GAN as well. Like it's very cumbersome, or optimizing GAN is very difficult. Then there is autoregressive image generation. On the left, actually, you can see a pixel CNN, where actually we can predict the next pixel based on the pixels already seen before. This one, like here, XI could be predicted based on all the previous pixels in the image. So this image is already available, right? So no, without requiring any label information, we can generate next pixel. And similarly, you all are familiar with GPT, ChatGPT, or GPT-4, right, the latest version. But they also actually did something like image GPT. So the first GPT-2 model was used. So they actually represented the image as the pixel sequences, very similar to text, the word by word sequence, and then they can predict the pixel, right? Very much like language modeling, where we can predict the next word based on what we seen before. So very similar to this pixel CNN. So looking at the previous pixels, the next pixel could be predicted, very similar to language modeling. And then imaging painting, where the image, input image can be masked and then the model will be to predict that mask, right? So there is an encoder and a decoder, and encoder features used through the channel-wise fully connected layer, passed to the decoder through the decoder to generate the mask, right? And the mask is already known, right? The image, so without requiring any label information, we can actually do this kind of pretext task. The masked autoencoder proposed last year, presented at Silvier, where they masked random patches from the image, and only the visible patches were passed through the transformer encoder, and then the representations were used along with the masked patches to pass to the decoder. Decoder is very simpler compared to the encoder, so that actually encourages the encoder to learn a more generalized representation. And finally, for the decoder, you can predict all the patches to reconstruct the original image. So this is again without any label information. So another interesting pretext task. And very similar, and it's very interesting that these two, this one and the previous one, were both published at last year's year. And another way to think of it, those two groups were doing this very similar thing at the same time. So this is also masked image modeling, or they call it simple masked image modeling, where just one single difference here. The previous one, here they didn't pass the masked patches to the encoder, but here they passed all the patches, masked or visible, all the patches were passed to the encoder, right? And then they used even simpler decoder to reconstruct the patches, like just one layer prediction after the encoder. So encoder could be anything like vision transformer or swing transformer. Then another pretext task could be just image colorization, right, from grayscale to RGB prediction. And this also yields a good representation, which is useful for different types of downstream tasks. Another interesting pretext task is split brain autoencoder, where compared to the traditional autoencoder, which takes the raw data, the image as input, and then reconstructs the image just through one encoder and decoder. Right? And in case of split brain autoencoder, it splits the original data into separate channels. Right? So raw data channels could be the raw data could be separated into two channels, like here, X1 and X2, and they are passed through the two different networks, encoder decoder, to get actually from X1 channel, the X2 channel is predicted, and from X2 channel, X1 channel is predicted, and from X1 and X2, the predicted X1 and X2, the final X, which is basically the original input, is reconstructed. And this also yields good representation and useful for downstream tasks. Another interesting pretext could be relative position learning. So randomly selecting randomly selecting this center patch, right, and then around that patch, 8 random patches are selected, and then along with the center patch, another patch from one of those 8 patches are passed to the model, and then the model will be able to predict the location of that path. So from the center path, right, the location of this path is 3. So this way, the model will be capable of learning useful representations. Then jigsaw puzzle. By solving jigsaw puzzle, we can also perform this type of pretext task for representation learning, self-supervised learning. Right, so here, 9 random patches are first selected, and then they are shuffled. Right, and then the shuffled patches are passed to the model, and then the model is trained to actually learn this to solve this puzzle. And by means of this, the model will learn the representation for various downstream tasks. And then in image transformation, like a rotation, we can also train a model to learn the rotation. So from the input image, you can actually perform these 4 different rotations. Right? 0 basically just the same image without any rotation, then rotating 90 degrees by 180 degrees or 270 degrees. So we can actually now treat this as 4-class classification problem, right? And then retrain the model on learning this rotation. And through this, the model will actually learn the semantic object representation, right? And when you use that pre-trained model for an actual downstream task, right? So classification of part type, maybe, then the model will be able to do that even from a limited level data. Okay, next, contrastive learning. So contrastive learning, there are many different variants of contrastive learning, but I will basically focusing on this. So from the input image, you can modify through some augmentations and then pass those both images, right, through the neural network for future representations, and then the representations are masked. So since those representations are coming from the same image, right, and then the goal is to minimize the distance between the representation. So this is very popular contrastive learning, simple contrastive learning or simpler. So where actually first batch, similar pairs in a batch are prepared. So by doing random augmentation of every image, so from the original input image we can create this pair, right, by performing random augmentation, right? Number of augmentations could be performed. And so actually the intuition is, even though those images are, those versions are augmented or transformed heavily, but still they contain the same content of the original image. So these 2 images are basically positive to each other. But for all other pairs, basically all other images in that batch should be negative. Example for the first image. So using that, you can pass the original image, 2 different versions, augmented versions of the original image through the 2 feature learning module encoder to get the representation and the project to this embedding space for the first image GI and then the second image J, and the goal is to maximize the agreement because they are coming from the same image. And by doing this, you can basically maximize the agreement for the positive examples, which are coming from the same image, and then minimize agreement between the representations of the example for the negative examples. And there is another type of contrastive learning. So the previous one we saw here is basically self-supervised contrastive learning. So it doesn't require any label information, but there is another type of contrastive learning, supervised contrastive learning, which actually leverages the labels or whatever is known to the model. So rather than using or waiting for the downstream task, if the label information are available, then we can actually use those information to guide the model for learning better representations during the pre-training stage. So that means images from the same class, they will be close to each other in the embedding space, and images from different classes, they will be far away in the embedding space. So using this contrastive learning, we can also pre-train medical image data. Right? So this work done by Google, so they actually use both pre-training on natural images and adding another stage of pre-training based on medical images. So both are contrastive learning. So self-supervised learning on unlabeled natural images first, then self-supervised learning or contrastive learning on medical images. So this is a publicly available data set. So, but this is their private data where they have images from the same patient or same medical condition. So those are used as two different examples of the same image or same patient, right? So we can treat those as positive to each other. So that means even though those are augmented and then passed through the encoder and projected to the embedding space, you can maximize the agreement between those two images. So this way, they call it multi-instance contrastive learning, and that way the model can perform better when evaluated on the downstream task. And then a popular CLIP model, contrastive language image pre-training, which actually leverages both text and image information through this multimodal contrastive learning strategy, where they actually try to maximize the representations for the images and the image and its corresponding text pair. So that means if there are n number of images in our data set, then there will be a number of along the diagonal, there will be n number of pairs, right, of image and text. And for those, the goal will be to maximize the agreement. But for others, right, the goal will be to minimize the agreement. And then they create this dataset classifier from the label text through the text encoder for all the classes, object classes, right, and then doing this zero-shot prediction. So without using any kind of label information, so just the goal is to align the image representation with its corresponding text representation. So all the text representation will be available from all the objects, right? And then for whichever the image and text pair, whichever pair will give the maximum agreement will be the final class. So you can also do a multimodal contrastive learning in medical imaging. So in medical imaging, while imaging, there is also a radiology report that becomes available, and you can actually pair the image and the report very similar to the CLIP model, right? So that means the same image and its corresponding text report should be similar, right? And they are aligned, and their representations are matched for this pretext task. And then during the downstream, you can just use the image encoder to perform the classification of this chest X-ray. Now, you can also use both pretext and downstream at the same time. That means joint training of the pretext and downstream. So this is one example of doing classification where we have the supervised branch. So for the images, we already have the label information rather than waiting for the downstream task. Through using the pre-trained model, we can do multitask learning. So and then there is this self-supervised branch, and through the augmentations, so some geometric transformations are performed, and then the model will be trained to predict that transformation. So, for example, rotation, flipping. And then finally, the loss can be calculated as the weighted sum of both supervised and self-supervised tasks. So similarly, we perform this joint pretext and downstream for both classification and segmentation of medical images at the same time. So we have this supervised branch and the self-supervised branch. Instead of one particular task, we have actually two tasks, classification and segmentation, and we perform this in an adversarial learning setup. So through the mask generator, we get the mask, predicted mask, and then we also use the original image with this to pass to the discriminator. And this discriminator doesn't just discriminate from real mask or the predicted mask along with the input image. It also predicts the class, so that we can also perform real class classification. And through the self-supervised branch, instead of the real class, you can actually predict the transformation, very similar to the previous one, right? But in case of segmentation, we don't have the label information for both class prediction and segmentation. But for the segmentation, we actually try to perform knowledge distillation. So by aligning the distribution of the mask, the logic-wise scores to the logic-wise score distribution in case of the label data. So this way we can actually calculate the unsupervised loss for the segmentation task as well. So just a quick report on the results, right? So we performed this for osteoporotic vertebra segmentation and also classification. So we extracted the patches, vertebra patches from the spine, lateral spine X-ray images, and then we perform the joint classification and segmentation with the pretext task within it. And you can see we can actually reduce at least 50%. So when we use the 50% label data, it already performing better compared to the fully supervised learning. This is the CNN. And similarly, in case of segmentation, this is for one particular example. You can see even at 5% label data, our proposed self-supervised, semi-supervised multitask learning still performs better than the fully supervised learning model. So we can save, reduce the annotation cost for 50% training data. So next, I'll be talking about image quality assessment. So, in case of CT, I was talking about the radiation exposure and to reduce the dose. Right? We need to reduce the dose for considering the patient safety. And when we reduce the dose, there will be noise incurring, and we cannot just reduce the dose linearly. So we need to better optimize the dose and image quality for optimal CT acquisition. And image quality assessment is a continuous process during the CT acquisition. So most of the image quality assessment techniques available are based on or reliant on the reference. So we want to perform the no reference, fully automated, fast and accurate, objective CT image quality assessment. So here you can see the same abdominal CT scan at different dose levels. So full dose, which is the regular routine dose, which is the expected one, but that uses 100% dose. So we want to reduce the dose, and if we keep reducing the dose, then you see noise will be increasing. And that will also hide some useful special context for certain pathology. So we checked the gradient SSI metric, which was found to be closer to a human visual system. So I will go into the details of this. But in our model, how we use the self-supervised learning. So we have this self-supervision and also the gradient SSI metric that we try to predict from the input image. And we also have this heat map loss. So we get the heat map predicted from the generated from the predicted quantification score, like saliency map, and then we compare against the error map, which is basically the difference in full dose and arbitrary low dose image. And then in case of self-supervision, so here our goal is to quantify the noise, or we are interested in doing the image quality assessment. So we just picked noise as noise level. We take the standard deviation of the image, which is already available. So we don't need any level information for that. But here again we perform like a joint training. So joint pretext and downstream. Some quick results, like when we perform this, we compare against the image reconstructed quantification model, and we can see that our self-supervised image quality assessment actually is very close to the reference in case of abdomen. And here we use the abdominal scans for training the model, but we didn't use the chest scans for training. So that is this cross-domain evaluation, and still the model predicts in agreement with the reference scores. This shows further classification, and when we compare against the SSIM scores from our predicted quantification scores. Next, another task, which is the image denoising. So in case of image denoising, our goal is just to predict the quantification score, the global score. Rather, we are interested in doing removing the noise. So if the image is acquired at 5% dose level or 25% dose level, we want to reach towards close to full dose. So from the CT, right, for the CT images, for better visualization, the physicians, when they review the images, the image readers, they actually select a window. So based on the anatomy, like for this one, abdominal scan, the window is selected like using two parameters, which are already available within the image metadata, window level and window center. So you can select the center and then how much wide you want. So that way, you can select the narrower window from it to better visualize the image. So you can see before window leveling and then after window leveling. So this is very simple task, but we try to use it as a pretext task. And it's very similar to image denoising, like our goal is to better visualize the image or remove the noise from it. So we use this as pretext task, and then our downstream task is to reach, get close to the full dose CT. So I won't go into the details of the model, but you can see we use the same architecture. So this is a very elegant way of doing it, like compared to other self-supervised learning techniques. You need to adjust the architecture or the loss function, hyperparameters, but here you don't need to adjust anything. Just pre-train on the learning that window level image, and then just fine-tune using the same architecture, same loss function, same hyperparameters. So just fine-tune for some infos and then we'll be done. Here are some results of even from 5% dose level. You see the original SSIM score, we could improve up to like 0.12 in this case for this pass, specific pass, and then for this image, whole image, we could improve up to almost 0.15, right, compared to other methods without our self-supervised window leveling. Okay, so the last one, CT image quality, CT organ dose estimation. So in case of CT, as I was talking about, reducing dose and optimizing dose and image quality. But in current dosimetric quantification, they do not actually consider patient body or anatomical structures, like different organs have different radio sensitivities, so those are not taken into consideration. But if we are interested, since we are interested in patient-specific dose estimation, And if we want to optimize the CT scan itself, right? So we want to do it before doing the actual CT scan. That means we need to do it prospectively before going to the scan. And to get the radius or organ-specific dose level, we need to predict it as at organ level, and then we also need to do it in real time. So starting with the scout acquisition, so when the patient lies on the bed for CT exam, first is X-ray-like image is taken. This is called scout. So sometimes one or both frontal or lateral scouts are taken, and then based on that, so those scouts are taken basically to prepare for the CT exam. So there is very little time between taking a scout and then the actual CT exam. So scout acquisition helps prepare for the CT scan by determining the scan length, then also patient body size. These scouts are also called localizers. So these are the actual patient data. So these contain useful information about the patient, like the different organs, or which organs, locations of different organs, and other things. But we can only calculate the dose, right, after doing the CT scan. So going through the all the steps, right? So finally doing the segmentation and on the dose map, we can actually get the organ-specific dose map, and by taking the mean score. So within one organ, dose usually remains uniform. So we can just take the mean dose. So then our goal is to predict this organ dose or mean organ dose, right? And the question is, can we predict the organ doses directly from the scout view? Okay, I will go into the details of this reference data calculation, like dose estimation. So we use the gold standard Monte Carlo, the faster implementation of it, Monte Carlo MCGPU, which takes the CT scan and through the density map and material map, it generates the dose map. And by performing the 3D segmentation and using that segmentation map, we can get the organ-specific dose map, and through that we can get the organ doses. Right, so this shows the distribution of the organ doses, the probability distribution. And this was our previous model for directly predicting the organ doses from the scout views, where we used the two scout views, frontal and lateral, and the scan lens, which is basically determined from the scout itself. So we have this feature learning model, which is the generic feature learning model, and then for every organ, individual organ, we have this individual dose learning module. So we predict the organ doses finally. So we calculate the L2 loss for every organ. But in this case, like, it's very difficult to collect the paired scout and CT scan data, right? And there are so many computations involved in it. So we could collect only 175 scans. So that's not a big number, right? So we are interested in improving the model performance. And if you think about contrastive learning, right? So there are so many augmentation strategies, and we cannot actually perform all those augmentations, considering the physical properties of the scan, like it could alter the patient position or other things like we cannot perform both horizontal and vertical flips. And then the contrastive learning or other self-supervised learning techniques, they rely on large number of unlabeled examples, right? So even collecting unlabeled data is a big challenge. And this Sinclair model, the simple contrastive learning representation technique, that actually requires large batch size, like 1024 images per batch to get the good performance. So which is not possible. You can like we only have 175 scans. So we were looking for some domain or task specific which include the multimodal information and which will still be realistic, right? So in our case, we have the scout views, right? Then what could be the second modality information for useful for CT dose estimation? So here something called patient water equivalent diameter. So using patient water cylinder phantom, patient water equivalent diameter is calculated, and that actually that's a good representation of the patient body size. So I didn't go into the details, but if you look at here closely, the DW, which is measured in centimeter, like this actually this figure shows that the CTDI, which is the CT dose index, so the metric for dosimetric quantification, then and size-specific dose estimate, so which is basically based on the DW. So both kind of follow the trend of the DW, like throughout the patient body location. So and it's also interesting that we can directly calculate to some extent the organ doses from the DW information itself, right? So we thought, okay, it could be a good second modality information, right? So it comes as a signal, 1D signal that actually could be available from the CT data itself. In the metadata we can get the DW information. So we actually perform this multimodal contrastive learning where we have the scout views and with the scan range, and we also use the exposure modulation table for tube current modulation, which actually controls the exposure, like from the MA and how the dose and this quality could be after performing the scan, right? And in the second encoder, we pass the DW for lateral and DW for the frontal scouts. So you can see these are just 1D signals, right? And this DW actually represents the patient body size. Since we are interested in performing patient-specific or personalized estimation, right? So we thought this kind of multimodal contrastive learning could be useful, right? So the intuition is when we have the scout and DW coming from the same patient, then they should be close in the vector or embedding space. And when the scout and DW, those are coming from different patients, then they should remain far away in the vector space. And we calculate the contrastive loss instead of having two different versions of the images, augmented versions, right? Here we have the representations from the scout views and then the representation from the DW, right? And that way we try to maximize the agreement for scout views and DW coming from the same patient. And this way we try to pre-train the model on learning this multimodal contrastive learning, and we fine-tune with our very similar model, right? So we use the encoder only from the scout view, so dropping the DW things altogether and predict the organ doses, right? So we can see that some improvement compared to without doing this contrastive pre-training. So overall we got 3% improvement, close to 3% improvement overall, and also consistently good R-square values for all 6 organs and the patient body. Okay, now the question is, okay, why does unsupervised learning actually help, right? So this paper published in 2010 actually they investigated with some experiments that supervised training is fraught with local minima, so even more so with than just a single layer neural network. And also random initialization, if we start training from scratch, those actually fall with very high probability local minima. But when we did the unsupervised pre-training, that actually initialized a deep architecture which lead to better generalization. So the conclusion was unsupervised learning. Pre-training could actually work as a regularizer. So that actually encourages better generalizability of the model. So here is some ongoing work in self-supervised learning. My group on liver segmentation, or we are also working on setting curriculum learning for diabetic retinopathy detection. Then we're also working on generative gynecology AI for bias mitigation in disease diagnosing the skin cancer. So future direction, so see, self-supervised learning is actually pushing AI limit, so there is no limit. It's limitless, we can go. And with self-supervised learning, we can reduce the annotation cost or requirement of label data, so, and we need less training cost, so it actually helps both economically and environmental benefit is there. And we can generate synthetic data, and since self-supervised learning only requires unlabeled data, right? So we can generate as many as possible synthetic data and pre-train on that. But we also need to have some quality check, right? So we can perform active learning to actually do the data, check the data quality, so we can identify which examples should be labeled by the human or the expert. And we saw a few examples right on performing joint pretext and downstream tasks. And in addition to that, we can also combine multiple pretext tasks. But the question is how or which pretext tasks will be joined, right? So that worth exploring. And then self-supervised learning, right? So the challenge is like specialistic or generalistic. Which way we should go, right? So you see that for general computer vision, right, is more generalistic, and then they always do not work for specific domains like medical imaging. Then we need to focus on the task or the domain itself. And with this figure on the right, you see Jan LeCun actually first defined the learning, machine learning as like the reinforcement learning, which is cherry on the top, then ice on the cake, which is supervised learning. So this is very few, and then little more, and then unsupervised learning, which is the cake. So that's enormous. But let us say, I now call it self-supervised learning because unsupervised is both loaded and confused term. So with that, I conclude, and the cake will still be here. Thank you.
We have a few any questions for the speaker? I have a question for you. It seems to me that you have to develop a lot of software for your work, and also you have to use software from other people. How do you get those software?
With the deep learning, so there is a framework like PyTorch, right? So and people share their pre-trained models. So most of the pre-trained pretext tasks I showed, right? So we can actually get a pre-trained model from others, and then even in our low resource setting, we can perform a specific training, fine-tuning on our data or particular task.
So if somebody is interested in your work or doing similar work or doing some kind of extension, can they get software from you?
Yeah, we can also share our code. People actually share their code on GitHub.
All right. Any other question? All right.
Just one question.
Yeah.
Should I hear from the difference between specialists and generalists in terms of data and algorithms? You can give us some ideas.
So specialistic versus generalistic.
Yes.
So in case of the general computer vision, right? So for example, if we do the contrastive learning, right? That's very generic representation learning, and that could be used for many different downstream tasks, like classification. We can just add fully connected layer during the fine tuning, and then we can also add decoder, right, to get the segmentation, right? So it can be for many different downstream tasks, but for specialists like a particular domain, for example, in medical imaging, right? So we need to focus on the particular task because we may not be able to do the exact same representation learning depending on our data settings.
All right. Then we thank the speaker for his interesting talk.
Thank you.